So this lecture is the beginning of chapter 2. In this particular lecture 1, we're going to discuss pressure and show how it varies within a static fluid, and then we're going to work a few examples. So first, let's define what pressure is. Pressure is a vector. Its magnitude is the force per unit area, and it acts in a direction perpendicular to the area. So we have a very small region of space. We can define it as the derivative of that F with respect to A, where A is the area. Over a larger surface, of course, we can define the average pressure as the total force over the area divided by the area. The units are the Newton per square meter, which is a Pascal, or it's the PSI, pounds per square inch is usually. You can define it as pounds per square feet. That's also another unit you see every now and then. So again, pressure is the normal force exerted by a fluid per unit area. The unit we try to use, if we can, is the Pascal, which is 1 Newton per square meter. But oftentimes you see a bar or atmosphere or other units being used. So here's a good example of the difference. Here you have a 150-pound man and you have a 300-pound man. They both have the same area, 50 square inches. So for the 150-pound man, he would exert 150 divided by 50, or 3 psi, right, pounds per square inch. Whereas the 300-pound man would exert twice that much because he weighs twice as much. So let's take a look at example 2.2. Here we have a pneumatic jack that's used in a service station. So you pull your car in and the guy hits the lever and lifts your car up so we can change the oil or change the tires. So here let's say we have a 5,000-pound car and we want to determine the force that must be developed by the compressor B to raise the lift at constant velocity. So here we're going to say air is in the line from B to A, and then we're going to neglect the weight of the air. Now typically, if it was oil or something like that, you couldn't do that, but in this example, he's going to use air. So he says the air line at B has a diameter of 1 inch, and the post at A has a diameter of 2 inches. 12 inches. So here we can calculate the pressure at A. So what's the pressure at A? It's going to be the force, which is 5,000 pounds, divided by the area of A, which is a cylinder, so it's going to be pi r squared. So half of 12 is 6 inches, so it's pi times 6 inches squared. So the pressure at A is 44.21 pounds per square inch. Now, here, if this thing, once it's lifted, the pressure at A has to be the same here as it is all the way back to here, because this is air, and we're neglecting the weight of the air. So the pressure at B is simply going to be the force at B divided by the area at B. But since the pressure is the same, the pressure of the A and pressure at B is the same, we have 44.21 pounds, which we found for the pressure at A, has to equal the force of the putting out by the compressor divided by its area, which is pi times its radius squared. So it's 0.5 inches squared. So you can solve for the force at B is 34.7 pounds. So this explains how 34.7 pounds exerted by the compressor can lift 5,000-pound car. Because of the way the lines are different areas, right? One term that often confuses students is the difference between absolute and gauge pressure. So let's imagine a container where we were able to take all the air out of the container. The pressure inside the container then would be zero, would be what's referred to as absolute zero, no pressure at all. So here at social scale, we start with absolute zero, no pressure. Any pressure that's measured above absolute zero is referred to as the absolute pressure, and we show that by a P with a little ABS symbol below it. So for example, standard atmospheric pressure is the absolute pressure of the atmosphere measured at sea level, and its value is 103.3 kilopascals, which is about 14.7 psi. That's referred to as pressure atmospheric. Now, any pressure measured above or below atmospheric pressure can also be referred to as what's called gauge pressure, and that's symbolized by P with a small g. Gauge often, and this is useful because gauges are often used to measure pressure relative to the atmospheric pressure. So if you're above atmospheric pressure, uh, you can simply add atmospheric pressure, the gauge pressure to find the absolute pressure, and if you're below that, you can subtract them to find it. So either way, the relationship between absolute pressure and gauge pressure is given to you by the following formula. P absolute is equal to P atmospheric plus P gauge. Um, Now you have to keep in mind that uh, absolute atmospheric pressures are always positive. However, the gauge pressure can be either positive or negative. So depending on if you're below atmospheric or you're above atmospheric. So let's take a look at example 2.2. Here we have a bicycle tire, and it's the air pressure from a gauge. We measure it. It's 10 psi. Let's say the local atmospheric pressure is 12.6 psi. Determine the absolute pressure in the tire and report the answer in pascals. So we can use the equation we saw before. The absolute pressure is the atmospheric pressure plus the gauge pressure. So we're told the atmospheric pressure and we're told the gauge pressure, so we can simply add those together and get 22.6 pounds per square inch. Now we have to convert pounds per square inch to pascals because that's what he wanted for the answer. So 22.6 pounds per square inch. First, let's convert uh, we'll convert the pounds to newtons. So there are 4.48 newtons per pound. So here the pound cancels and we're left with newtons. Now these two terms will convert the square inches to square meters. So first let's convert square inches to feet, and then we'll convert the feet to meters. So there's 12 inches in 1 foot, and 1 foot is 0.3048 meters. So when you divide it out, you'll have the inches squared will cancel, you'll be left with foot square, and the foot squares will cancel, you'll be left with meter squared. So we get 1.5 or 155.81 times 10 to the third newtons per square meter. So the newtons per square meter, that's a pascal. 10 to the third is a kilo. So we'll report our answer as 156 kilopascals. When the variation of density with elevation is known, we can calculate how the pressure varies within a static fluid. So here we have a case where we have a fluid and we have two depths within the fluid. So we have a Z1 and Z2. So Z2 is at the higher elevation and Z1 is at the lower elevation. So we can calculate here, the pressure, there's going to be a pressure difference. So the pressure difference is given by the negative integral of rho g dz. So here the negative sign indicates that the pressure will decrease as one moves upwards in the fluid in the positive z direction. So in other words, here P2 is going to be less than P1, so we put a negative sign here. So this formula applies to both incompressible and compressible fluids. Now if we have a incompressible fluid, as in the case of most liquids, then its density is constant. So in our equation above, we can factor out the density and then integrate. So here we have water, for example. If we start up here where Z is 0, this is atmospheric pressure, and integrate down to some value of Z, well, the density is constant, so we can pull it outside the integral. G is constant, so we can pull it outside the integral. So we end up with the pressure at the surface, which is P0, plus rho G times the H. And here the negative sign takes care of it, makes this a positive. So typically in this particular textbook, he replaces rho times G, which is a constant, by this gamma symbol. In particular, if the P0 is atmospheric pressure, then this pressure at depth is going to be atmospheric plus this term here. So that's just our term for our gauge pressure. So you have atmospheric plus gauge pressure is the pressure here. So The gauge pressure at depth is just gamma times H. Now, if we solve the previous equation for H, we get pressure divided by gamma. And this is often referred to as what's called the pressure head. And what this indicates, it indicates the height of a column of liquid that produces the gauge pressure. So for example, let's say the gauge pressure is 50 kilopascals. Then the pressure heads for water and mercury can be calculated as follows. Gamma for water is 9.8 times 10 to the third newtons per cubic meter, so we can divide those and get 5.10. For mercury, it's much less because the gamma is much bigger here, so it's 0.376 meters. So in other words, a column of water that's 5.10 meters high would have a pressure at the bottom of 50 kilopascals, but it would only take a 0.376 meter column of mercury to yield the same pressure because mercury is much more dense. So here's a great example, and this gets us started into being able to solve some problems with multiple liquids at different layers. So here we have a tank and a drain pipe shown that's filled with gasoline and glycerin. Well, gasoline is lighter than glycerin, so it floats to the top. So let's say once it's settled, we have 2 feet of gasoline on top of 3 feet of glycerin. What we want to know is what's the pressure at the drain plug C. And so we're going to use the fact that gasoline has a gamma of 45.3 pounds per cubic feet and glycerin has a gamma of 78.7 pounds per cubic feet. So the pressure at the bottom is simply going to be the pressure due to the gasoline, which is going to, so for example, we start up here at top, that's atmospheric, so we add gamma gasoline times the height from A to B, which is 2 feet, plus we add to that the pressure due to the glycerin, which is gamma of glycerin times the height from B to C. So the bottom pressure is going to be the sum of those two pressures. So here I've calculated what that is, and it turns out it's 326.7 pounds per cubic feet, which is 2.27 psi. And here I converted pounds per cubic feet to psi. You can find those conversions either in the front or the back of the textbook. So he wants us to report this as the pressure head. So here we have to calculate what the pressure head is. So it's 326.7 pounds per square feet divided by the gamma for water, 62.4 pounds per cubic feet, and we get 5.24 feet as the pressure head at the bottom of the pitcock at sea. When we have a fluid that is compressible, we have to go to much more extremes to actually be able to calculate the pressure difference. So, for example, in the case of a gas, its specific heat gamma, specific weight gamma will not be constant throughout the fluid. Therefore, to obtain the pressure, we have to integrate dP, which is equal to minus gamma dz. But this requires us knowing gamma as a function of pressure. So, for an ideal gas, it's pretty simple. We have pressure equals rho RT, so we can plug that in, solve for gamma. Gamma is rho times G, so we can plug in for the rho term. Rho is P over RT. We can plug that in for gamma, and then finally solve the equation, integrate. So we got P on this side, divide both sides by P. So we got P on this side, G over RT is a constant. We can integrate both sides, from P0 to some final pressure, Z0 to some value Z, and we can integrate this to solve for what we need if we know what the temperature is as a function of Z. But if it's constant, it's pretty easy. We can pull that outside. But if it's a function, it may be a function of Z. So we'll have, in that case, we'd have to know what that was. So let's take a look at, for atmosphere, it's pretty simple. Let's assume that it remains constant. Let's assume that the T is constant, so we replace T by T0. We can pull that out, and this is just, the left-hand side is simply a natural log, and this one's simply a linear function. So we can invert this and solve for P, and it turns out it's an exponential function. So if you actually plot what this is for the atmosphere, you can show that in the troposphere, the lowest part of the atmosphere, near the surface of the Earth, it follows like this, and then kind of goes straight, and then goes up, heats up drastically through the stratosphere into the thermosphere. So this is sort of how this is done for the case where the specific weight is not a constant. So how do you measure pressures? Well, often there's several ways when engineers do it to measure not only the absolute pressure but the gauge pressure. And our book goes through several examples. I'm going to touch on two of them. One is what's known as the barometer, because that's pretty easy to measure. Basically, the early barometers were simply you had a liquid of mercury, you took a test tube, you filled it up and inverted it, and so the pressure head, as we figured out in the previous slide, so outside you have the pressure, atmospheric pressure pushing down on it. It's going to push up the mercury inside the test tube, and so you can write simply equation here that PB equals PA plus gamma H, where gamma is the specific weight of the mercury. Now PA, that's if you do this right, this is going to be a vacuum, so that's going to be 0. And so the atmospheric pressure is simply gamma times H. So normally the height of H is stated in either millimeters or inches of mercury. So, typically you calculate this out, it's about 29.9 inches of mercury, or 760 millimeters of mercury. That's about what standard atmospheric pressure turns out to be. Another device that's often used to measure the gauge pressure in a liquid is the manometer. So a manometer is simply a tube filled with a liquid. So in order to determine the pressure at any point, we can use what's known as the manometer rule, which is basically two parts. So first of all, in this example, we have two liquids. We have a blue liquid and we have a gray liquid. So maybe the blue liquid's water and the gray liquid is mercury. So here, if we want to determine the pressure at A, this manometer rule works as follows. Well, first of all, if you move horizontally in the same fluid, it has a constant pressure. So for example, the pressure at A here is the same as the pressure here because we've moved horizontally. Now you can think about that as, as you go down, you gain pressure, and you go up, you lose pressure, but you've gained as much as you've lost, and so the pressure here at this point has to be the same as the pressure there. Now that's the first part of the manometer rule. The other part says if you go up in elevation, you lose pressure given by gamma times the height difference. And then when you change interface, here again, you have a different gamma. So, so basically, the two parts are if you move horizontally in the same fluid, the pressure stays the same. If you go down, the pressure increases. If you go up, the pressure decreases by an amount equal to gamma times the height difference. So let's take a look in the next example at a very specific example. So here, for example, let's start here and let's assume that the pressure at point C is 0. So we start here at A, so the pressure here is PA. We move across horizontally here, which is the same pressure. Then we go up, so the pressure decreases by an amount equal to gamma times the HAB. Then we move up again, and the pressure decreases by an amount gamma prime times HBC. So gamma is the specific weight of the blue liquid, and gamma prime is the specific weight of the gray liquid. So we can solve this, we get up to atmospheric here, it's 0. So we can solve this for P of A. All we need to know is the gamma, gamma prime, and HAB and HBC. We can solve it. So let's apply the manometer rule to a simple example. So here we want to determine the pressure difference between A and B we have two different fluids. We have a green fluid and a kind of like a lime green fluid. The density of the liquid in AC, so from green liquid here, and B to D is 800 kilograms per cubic meter. And the density in the lime green fluid from D to C is 1100 kilograms per cubic meter. So here we're also told the distances, right? So let's start at B and simply walk our way around to A. So remember, the manometer rule has two parts. If you move horizontally in the same fluid, the pressure stays the same. If you move vertically, you have to account for the pressures by multiplying the density times gravity times the change in height. So start at B, we're going to move up to here. Why here? Well, because if we find the pressure here, we can simply jump across to D, right? So that'll be the same pressure here as it is at D because we're moving horizontally in the same fluid. So what's the pressure here? We're moving upwards. So the pressure is going to go down. So it's going to be minus rho 1 times G times the height difference from B to here, which we know is 0.250. So look at our equation. So we started at B. We go down, so it's minus rho 1G times the height from B to D, which we know is 0.25 meters. So now we know what the pressure is here. So we want to move to here. So how are we going to do that? Let's move down to here, and then we can move horizontally because, again, the pressure is the same here as it is there. So what's the pressure difference between here and here? It's the density of the lime green, rho 2, times G, times this height differential, which is 65 millimeters, right? So we add on, because we move downward, rho 2, the density of the lime green, times G times the height from D to C, here to there. So now we're over here because we can move horizontally. Now we want to find the pressure here. So here the pressure is the same as it is here because, again, we're moving horizontally. The pressure here is the same as it is there. And then we're going to move down, so we're going to subtract density 1 times G times the height difference from here to there, which is 30 millimeters. So that adds on the other term, and then when we get to here, that's equal to the pressure. So we can find the pressure difference. We can just move this term to the other side. So delta P is PA minus PB, and then we can put the equations around and write them this way here. So here, if you plug in the quantities, rho 1, rho 2, G, and the different heights, you can calculate this. It turns out it's negative 1.03 kilopascals. So I encourage you to plug these values in and calculate it and see if you can calculate that. Another thing I encourage you to do, in our example, we started here and worked our way around, but if you start here and work your way around, you should get exactly the same answer. So give that a try.